So let us talk about geometric optics, and this all we are going to see. So a ray of light is an extremely narrow beam of light, and all visible objects emit or reflect light rays in all directions. So our eyes detect light rays and we think we see objects. We really see images. Images are formed when light rays converge. This is how we see the image. So converge means come together, and when light rays go straight into our eyes, we see an image in the same point as the object. So it is possible to see images when converging light rays reflect off meters. This is reflection, means bouncing light. Reflection is when light changes direction by bouncing off a surface, and this is the surface. So when light is reflected off a mirror, it hits the mirror at the same angle, this theta I, the incident angle, and this is theta R, the reflected angle. So the normal is an imaginary line which lies at right angles to the mirrors where the ray hits it. So mirrors reflect light rays. So how do we see images in mirrors? This is how it takes place. Object is like that. This is the image. Light from the object reflects off the mirror and converges to form an image. So we perceive all light rays as if they come straight from an object. The imaginary light rays that we think we see are called sight lines. This is the dotted line. These are the dotted to show the imaginary light rays. So these are the image types. Real images are formed by light rays, and virtual images are formed by sight lines. Again, these are the dotted lines, and these are the plane of flat mirrors. So images are virtual, that is formed by sight lines, and upright images are not magnified, means object H0 is always equal to object Hi, and object distance D0 equals to the image distance Di. Then coming to spherical mirrors, concave and convex. Concave, just a part of a sphere. This is a sphere, so C, the center point of the sphere, R, the radius of curvature, just the radius of the sphere, F, focal point in or of the mirror or lens, that is halfway between C and the sphere, and the focal distance F is equal to R by 2. So concave mirrors, this is caved in, this is the optical axis. So light rays that come in parallel to the optical axis reflect through the focal point. The first ray comes in parallel to the optical axis and reflects through the focal point. The second ray comes through the focal point and reflects parallel to the optical axis. So a real image forms when the light rays converge. This is the example of concave mirror, example 2. This is the optical axis. So first ray comes in parallel to the optical axis and reflects through the focal point. And the second ray comes through the focal point and reflects parallel to the optical axis. So the image forms where the ray converge, or they don't seem to converge. The virtual image forms where the sight rays converge. So now let us see that this is an object, this is a concave mirror. Mirrors are thin enough that you just draw a line to represent the mirror. So locate the image of the arrow. This is the image of the arrow. Because one lies, it goes to the focal point, and another goes from focal point and reflected and these two intersect at this particular juncture. So the convex mirror, these are curved out, and this is the focal point, this is the optical axis. So light rays that comes in parallel to the optical axis reflect from the focal point. And the focal point is considered virtual since sight lines, not the light rays, go through it. The first ray comes in parallel to the optical axis and reflects to the focal point, and the second ray comes through the focal point and reflects parallel to the optical axis. And when we join them, the light ray don't converge, but the sight lines do. So the virtual image forms where the sight lines converge. Now you have this object, you have this F focus point. Now locate the image of the arrow. This is the image with these sight lines. So lens and mirror equation, 1 by f is equal to 1 by di plus 1 by d0. This f is what? Your focal length. d0 is object distance, and this di is image distance. So f is negative for diverging mirrors and lenses, and di is negative when the image is behind the lens or mirror. So you have to choose the this sign accordingly. Magnification equation, m is equal to hi by h0. This is equal to minus di by d0, where m is the magnification, hi is the image height, ho is the object height. So the height is negative, the image is upside down. If the magnification is negative, the image is inverted, that is upside down. Now coming to refraction, that is bending of light. Refraction is when light bends as it passes from one medium into another. So when light traveling from air passes into the glass block, it is refracted towards the normal. This is the normal. And when light passes back out of the glass into the air, it is refracted again away from the normal. So since light refracts when it changes medium, it can be aimed, means lenses are shaped, so light is aimed at a focal point. The lenses, the first telescope designed and built by Galileo, used lenses to focus light from faraway objects into Galileo's eyes. So his telescope consisted of a concave lens and a convex lens. This was the convex lens, this was the concave lens. So light far away from object, and light rays are always refracted towards the thickest part of the lens. So concave lenses are thin in the middle like this and make light ray diverge, that is spread out. So if the rays of light are traced back, these dotted sight lines, they all intersect at the focal point, right behind the lens. So these are the concave lens. This is how light comes, and this is how it goes. So the light rays that come in parallel to the optical axis diverge from focal point, and the light ray behave in the same way if you ignore the thickness of the lens, right? The light rays that come in parallel to the optical axis still diverge from the focal point. This is the concave lens example. The first ray comes in parallel to the optical axis and refracts from the focal point, right? The second ray goes straight through the center of the lens. This is how. And the light rays don't converge, but the sight lines does. These two. The virtual image forms where the sight lines converge. Now, this is the object. This is how it will be seen if it is a concave lens. This will be the image, because this is how it is going. This is refracting, or you can say it is diverging, and here we have the light or sight line going or coming from F. So this is the point where it is actually intersecting. So convex lenses are thicker in the middle and focus light rays to a focal point in front of the lens. This is the focus. The focus or focal length of the image is the distance between the center of the lens and the point where the light rays are focused. Convex lenses. These are the optical axis. This is the focus. So light rays that comes in parallel to the optical axis converge at the focal point. This is again an example. The first ray comes in parallel to the optical axis and refracts through the focal point. Second ray goes straight through the center of the lens, and the light ray don't converge, but the sight lines does. So this is the virtual image which is formed when the sight line converge. Now let us take this example. We have object. This is a convex lens. The lenses, the location of the image at the arrow will be like this, right? This is our refracted image from the focus, and this is directly from the center of the lens. Thank you so much. This was the very basic idea about lenses.